Welcome to the Biosphere 2, the world's largest enclosed mesocosm dedicated to reef research. I know everybody in this class, 412B, signed up for a wonderful oceanographic field trip in Southern California. But today we're going to do a little compromise given the situation and introduce you guys to a lot of the concepts that you would have become familiar with on that field trip here at the Biosphere 2 ocean. But first we want to give you a little bit of an overview about why the Biosphere 2 is here and why it is so important. So as we'll talk about in a couple weeks, the coral reefs worldwide are really in dire straits. We've lost an estimated 50% of the world's reefs, and we're really at risk of losing them entirely if we continue to do nothing. But I'm here, I moved from Boston to Tucson in the middle of the Sonoran Desert to study coral reefs because I think there's a tremendous amount of hope. And our team is really applying what we've learned out of decades of coral reef science, where we've really come together as a community to figure out what the key building blocks of coral reef resilience. And we haven't really introduced the term resilience yet in class, but what I mean by resilience is the ability for an ecosystem like coral reefs to recover from a disturbance. And that coral reef ecosystem might not look like the coral reefs that we knew before, but it'll be able to persist through continued changing ocean conditions. The reason why coral reef resilience in particular is important is because coral reefs provide an estimated $1.2 trillion of critical goods and services every single year. We might be far removed here in the Sonoran Desert, but they still impact us. As we saw in class, we get our critical weather, particularly our winter rains, from the oceans and ultimately far removed by Pineapple Express type events that come from the middle of the Central Pacific where coral reefs reside. So together with our team of over 50 collaborators from all over the world, we're trying to move past this decades of research on process and move towards solutions. Because of course with global pandemic and ecosystems collapsing all over the world, it's not the time to sit in our labs and try to figure out what's happening. It's the time to figure out how we can do something about it. Just like right now, we are really in real time coming up with solutions for COVID-19. So our team, fortunately, is comprised of a number of brilliant coral reef scientists who've come up with solutions that are truly innovative for protecting coral reef ecosystems. So for example, in class, I introduced the coral reefs in areas that have been frequently hit really hard at a every few year pace by really warm temperatures associated with El Nino events. Those reefs, just like me as a Minnesotan in theory, are better at handling cold. Those reefs are more resilient to these warming events. So one of the solutions that has been created is that we can actually warm up the temperatures, and we'll show you one of the experimental raceways where we're doing some of this research right here. We can warm up the temperatures and stress the corals out. Purposefully warm the temperature, cause coral bleaching, and then reintroduce them onto the reef. And what this does is it increases the resistance of those corals to future coral bleaching events. There's other types of solutions that are a little bit more risky and more innovative, like even adding probiotics. So much like we take probiotic pills to help with stomach ailments, we can give coral reefs probiotics that'll make them more resistant to diseases and other stressors that reduce their resistance to these global climate change related stressors. So just to wrap up, why the Biosphere 2? So obviously there's a number of solutions that are being developed and implemented worldwide on the reefs. So for example, our colleagues in Marine Laboratory in Florida are already transplanting tens of thousands of corals onto the coral reef tract right now to rebuild that decimated coral reef ecosystem. But what we don't know is how those corals will survive as the oceans continue to change. What corals will do well and what corals will not survive. So this reef behind me, the Biosphere 2 ocean, is a critical testbed for these solutions for two key reasons. One, it's obviously a huge scale, 700,000 gallons or 2.6 million liters. So this means that we can test these solutions at ecosystem scale, meaning that the ecosystems all the way from the viruses and the bacteria all the way up to the fish consumers can be studied in real time. And we know from growing evidence that those tiny little microbes that we can't see are really critical for reef health. And so we need an entire reef ecosystem to fully understand these complex dynamics. The second key reason is control. We have, despite its scale, the ability to very precisely manipulate the temperature and even the pH of the ocean conditions in this reef behind me. So unfortunately, much of this technology was from the 1990s when the Biosphere 2 was first built. So myself and our team have been working tirelessly over the last few years to re-engineer this system, to bring it from 1990s technology to 2020s technology. And we're really excited to have just installed a new, what we call heat exchanger. And this heat exchanger, which we'll show you a little bit later, allows us to precisely manipulate temperature at about 1 to 2 degrees Celsius change per day at 700,000 gallons. So that's a hugely powerful system, and it'll allow us to test not only current conditions, but projected future warming. The other thing that we're working on is to change the CO2 or the pH of the system. Right here at the Biosphere 2, some of the most seminal research on ocean acidification happened by Chris Langdon of Columbia University. And because of his experiments, we know that coral reefs grow up to 40% slower as a result of ocean acidification. So as we upgrade these systems to bubble in CO2 and project future ocean acidification, we'll be able to test at ecosystem scale how these solutions respond to warming and ocean acidification right here in the Sonoran Desert.
Hi everyone, my name is Katie Morgan. I am Manager of Marine Systems out here at Biosphere 2. Diane gave you a little bit of an intro to this amazing system we have here, and I'm going to tell you a little bit more about what we've been doing in the last year to really bioremediate this system. So after some of the really initial experiments they did with Columbia, they looked at CO2 and the effect of increased CO2 on corals. And after that period of time, the corals were incredibly stressed out, and most of them did not end up surviving. And so what we have is what we consider a degraded reef system. So this is what we see as an immense opportunity as scientists to understand what's going on in the degraded system and take all the data we can and then track it as it goes from a degraded system back up to a healthy reef before we stress it out again with the experiments that we plan to do. But the process of going from a degraded reef back to a healthy reef is not an easy one, and we've been tracking that as we've gone, and we had a lot of algae in the system. So we've actually pulled about 10,000 pounds of algae out of here by hand since June. So that's been quite fun, but also quite a lot of work. So we can't physically do that all the time, and we need something in the system to help us balance that algae that inevitably will grow back. There's always going to be a healthy balance in this system. So we have introduced some key herbivores to the ocean. That comes in many different forms. So we've got some hermit crabs, we've got some top crown snails. We also have one of my favorite animals that I'm actually going to pull out here for you. This is a black long spine diadema. So it is a sea urchin, and these guys are also really excellent algae eaters. So we have these along with some short spine sea urchins that live in this ocean and help eat that algae. So they really keep it at a balance. On top of the urchins, which I would argue are probably the champion algae eaters. So these are our red-legged hermit crabs. These are one of the animals that we have in here that are great herbivores. They're really successful at eating, especially along the beach here, along the shorelines. And then we find them towards the top of some of the rocks in the deeper ends. So if there's a wave break, they tend to be on that top area of the rocks. They're great intertidal animals. So likely if you were to go tide pooling in California, you would definitely run into some of these guys. So this is a top crown snail. So this is one more example of the herbivores that we've added into this Biosphere 2 ocean. These guys are very cool. He's starting to come out here. Also really great algae eaters. So they kind of take care of, they kind of clean up after all the other organisms that make a mess when they go along. These guys are what we consider the polishers. So they come along and really polish off the rocks. You can see him moving in and out. This is his foot right here. So they can be pretty strong on those rocks and just kind of slide along as they are able to eat up that algae. We also have some fish. So this ocean has had fish in it here and there. We had some species or some descendants of fish that were added in 1996, but there had been no new fish additions since then. So actually last April, we added the first fish since 1996. That was a really big day for us. We had to go to the airport and pick up these fish at the, at the shipping container area, and the guy was really confused about why we were picking up fish in the middle of the Sonoran Desert. Brought them out here. It took us about 10 hours to acclimate them to the system, and they are thriving and surviving in this ocean, helping us eat the algae. So we added about 22 fish. 20 of them were ocean surgeonfish, and 2 of them were red-banded parrotfish. So these are some of the fish that we've identified as ones that will work in a community. So we are developing a community inside of the Biosphere 2 ocean that we will study. When we study the corals, we'll also study everything else, from the nutrients to animals like this black long spine, to the fish, to the microorganisms in the water column. So we've talked a lot about what we've done in the past few years to really understand the system and to bioremediate it. So we consider that phase really kind of done. I mean, we're going to have to continue to bioremediate as we move forward. But our next phase, as we move into it, is adding corals into the system. So we've removed all this algae. We have a healthy biomass of animals in here helping us out. And now we feel like we're ready for corals.
So this is the titanium plate and frame heat exchanger that I talked about earlier. So the way this works is that water is passed along titanium plates that are filled with hot or cold water, and then subsequently heat or cool down that water that's recirculated back into the main Biosphere 2 ocean tank. So this massive heat exchanger, the latest, the state-of-the-art technology, like I said, can warm that ocean or cool it down at rates of 2 degrees Celsius per day at 700,000 gallons of flow through the entire system. So this will really allow us to test future conditions on coral reef ecosystems worldwide and understand how these solutions might work under changing ocean conditions. The other key piece of this new heat exchanger are a series of filtration systems. So we have 6 filters here, each of which have a bag. This is a 250 micron net. Each one of these then captures large particles of algae and other things that make it through the filtration system so that they don't get caught in a really nice, expensive plate and frame heat exchanger. But we picked this particular size net because it still allows most of our phytoplankton and zooplankton, as well as bacteria and viruses, to pass back through the system so that we can continue to study the microbial dynamics, larval dispersal, and other key questions related to coral reef ecosystems here at the Biosphere 2. This is our coral reef raceway system. It's a 2,700-liter aquarium that's dedicated to experimental manipulations of coral reefs and other coral reef organisms. It has its own life support systems, much like the ones I described for the Biosphere 2 ocean. So it has recirculating water that pass over here through a heat exchanger, as well as a protein fractionator to get rid of organic matter and other contaminants within the water, as well as the sand filter that again helps remove some of the metals and other contaminants that might build up within the water system. So with that heat exchanger, like our main tank, we can manipulate the temperature and even pH of the water in this system. This is where we will do the tests of our coral reef solutions before we transplant them at ecosystem scale into the Biosphere 2 ocean. So for example, we can turn up the knob and the temperature and really warm this experimental system, stress the corals out, and look at bleaching responses among species and among species with different symbiotic zooxanthellae in their tissue, and look at how then those responses respond at an ecosystem scale in the Biosphere 2. Another thing that we might do with these raceways is that probiotic experiments that we talk about. Because these systems are isolated and we're going to have up to 5 replicant tanks, we can test various probiotic solutions, different communities of beneficial microorganisms, and how they impact the resistance and resilience of coral reef organisms. So we got support for this raceway thanks to a generous donation of one of our supporters, and are currently ordering a second one that'll go right here next to me. And over the next hopefully year or maybe a few years, we're going to have 5 of these systems right here in the scrubber room to really build this coral reef resilience program here at the Biosphere 2. To prepare for the introduction of corals into this raceway, we set up this tank with a mix of Biosphere 2 ocean water as well as instant seawater that we created from salt and RO water. We also, down here below us, inoculated this water with what we call live rock. This live rock has critical microorganisms, bacteria and other beneficial microorganisms for coral reefs that corals depend on to be healthy. And so the combination of the microorganisms living in the Biosphere 2 ocean water that we inoculated the system with and this live rock will stabilize this ecosystem and prepare the water clarity, the water chemistry, and the pH for the introduction of corals in the coming weeks. So in class we talked about CTD, or conductivity temperature depth profiling. So on the oceanographic vessel that we would have gone on in Southern California, we would have gotten to see one of these, what we call a rosette. And a rosette has one of these CTD instruments on the bottom of this big metal ring. And in that metal ring are also water bottles. So what we can do is we can lower it slowly to create a depth profile of temperature, dissolved oxygen, and conductivity, and a number of other specific parameters that can be adjusted depending on research interests. And we can identify parts of that profile that are of interest for whatever our research question is. So for example, let's say we're really interested in the oxygen minimum zone that we talked about in class. So we might see a big drop in oxygen in the profile, and we might want to collect a water sample from that depth. So we could deploy one of these water samplers, which would grab a sample of water, and when we bring that rosette back up to the surface, we not only have our profile of temperature, conductivity, and other parameters, but we'd also have a number of water samples. So unfortunately, we're not going to get to do a rosette today, but we will do 2 similar devices that are very similar and are more versatile because they're handheld and can be brought wherever you go in the field. So we use both of these devices frequently. The first is called a YSI. It's the company, it's like the Kleenex brand of sondes. This device can be set up to measure a number of different physiochemical parameters, so physical and chemical parameters at depth on the particular system of interest. So I'll open up this casing that's used to protect the sensors and show you those 4 sensors. So this is the temperature and conductivity sensor, dissolved oxygen, pH, and ORP, which measures the redox potential, so the ability of the water to oxidize or reduce chemicals. And you can see it trying to log the data of the air here. And one of the nice things about the Professional Pro series that we have here is it actually tells you when the value stabilized. So you'll see a lot of things blinking because it's not sure what the value of conductivity of the air is, which is probably okay, right? So this 30-meter long cable has markings every meter, so we can get a profile with depth. So I'm going to slowly lower this in until that black marking is at the water column, right there. Turn our instrument on and wait for it to stabilize. While it stabilizes, remember from lecture that conductivity, specific conductivity, is the ability of water to move an electric charge. From temperature at a particular environment, or specific conductivity, which is at 25 degrees Celsius, we can measure the salinity, the total dissolved solids, and other related parameters here at the Biosphere 2 ocean. So, for example, now that all of the numbers have stabilized, the ocean right now is 23.9 degrees Celsius. The dissolved oxygen is 93.7, meaning that it's almost fully saturated, which would be 100% oxygen. The specific conductivity is 50,255 microsiemens, which at the current temperature then is a conductivity of 49,000 microsiemens per centimeter. What this means in terms that we all understand commonly with ocean salinity of the Biosphere 2 ocean is about 33 parts per thousand, or PSU, practical salinity units, as we talked about in class. And this is really typical of coral reef environments in the tropics, around 32, 33, or 34 parts per thousand. Using the temperature and conductivity data, we can also determine the total dissolved solids, as well as, of course, the conductivity, which is the raw reading that's used to calculate these two parameters. And finally, you can see that we do have an oxic environment. We have a dissolved oxygen concentration, or percentage, of around 90% right now. It's dropping a bit as we've left it in the water for a while. But it's very close to 100 in most conditions, meaning that it is really well oxygenated at the surface. The current pH in the ocean is 8.33, which is common for coral reef ecosystems. They're typically around 8.2 or 8.3. And finally, ORP is 83.3. An ORP value of greater than 0 indicates that it's an oxidizing environment, meaning that there's plenty of free oxygen to oxidize organic matter and other chemicals within the water column. And with that, we've taken our YSI readings. The second key piece that we'll use that will replace the rosette of that CTD is what's called a Van Doorn. This device was named after William Van Doorn of Scripps Institute of Oceanography, and it's a very handy device for collecting water samples at various depths in the water column. The way it works, and we'll show you how it works out on the boat here in a second, is that we have these two seals on either end with a nice rubber gasket in between. We can open up each of these ends of the trap. This one's a little bit loose. I think the gasket needs to be replaced. And then we have what is called a bullet. And we send the bullet down by rope. It hits this trap mechanism and it closes the two gaskets, capturing the water inside. So with this, we can collect a water sample at any depth in the water column that we want. This device is called a horizontal sampler because it's collecting water moving horizontally down with depth. In order to get a clean water sample, when we get to the depths of interest, we move the device horizontally to clean it out, of course, with the gaskets open. This allows us to look at the chemical constituents, for example, those critical nutrients that we talked about in class, at every depth in the water column of interest. Okay, we're going to do it very shallow so you guys can see. But obviously I would lower this to the depth that I wanted to collect the water sample from. And then I will slowly make sure that I move to a different part. So in this case, I'm going to move close to the camera just to demonstrate. To rinse out the bottle and then deploy the bullet. And then slowly lift it back up with this crappy rope. And like I said, no surprise, we didn't get a good seal. Tell Professor Cohen he needs to replace his rubber gaskets. But you can imagine now that we have collected a water sample successfully, and we can use the spigot to fill our water sample from the depths that we collected. One other quick thing that I didn't demonstrate for the sake of time is that the other thing that we would do if we were actually collecting this water sample is that we'd rinse the Van Doren bucket before we deployed it at depth. So we'd go down, rinse it once, put it back in the water, rinse it twice, and a third time before we collected our water sample. So this way we know that whatever we collected in the water sampler before has been rinsed by the current water that we're interested in sampling. So this is a wonderful handmade Secchi disc that Andy Cohen made, our other instructor. But it works the same as any other Secchi disc. You'll notice that it has alternating black and white quadrants that are used to visualize the turbidity and visibility going down with depth in the water column. Of course, there is also a weight on the bottom so that it sinks easily through the water. So what you'll see me do, and the way this works, is first we'll take note of the weather conditions. How much sunlight there is, cloud cover, visibility on the ocean. And as Andy talked about in class, this is really critical because the depth at which we can see the Secchi disc is going to be dependent on the time of day and the amount of sunlight that day based on the weather conditions. So what we'll do is we'll slowly lower this in the water column. Our rope here is marked every meter so we know how deep we've dropped the Secchi discs in the water. And we'll do it until, let's imagine, we can no longer see the Secchi disc. And we write that depth down. That's our first reading. Then we'll raise it back up until we see it again. And that's our second reading. And if we average those two depths together, we get our Secchi depth reading. And this is how we determine visibility in the water column, turbidity, productivity, and other factors that impact that visibility. All right, here we go. Oh, we've hit the bottom. So in this case, our Secchi reading is actually deeper than the depth of our water column. So we'd have to record that it's greater than about 2 meters depth because the water clarity in the Biosphere 2 is really high. And it's right at this point beneath me, it's probably only about a few meters deep because we're right near the reef crest, which is the shallowest part of the Biosphere 2 ocean. So unfortunately today we won't get a very good demonstration of the Secchi disc, but you can see how the concept works. The last thing that we're going to do is a plankton tow. So of course the other parameters here that we're measuring are mostly focused on the physiochemical profiles of the water column. So this is where we get at what's happening with the biological portion, the productivity, both in terms of phytoplankton and zooplankton in the water column. This particular plankton net is used for zooplankton. It's a 100-micron mesh, and the way it works is it's towed very slowly behind a boat from this sampling ring. This ring here directs water through this fine 100-micron mesh and to what we call the caudal end, the cod end of the sampler here, that'll connect, and all of the plankton, the zooplankton, will get caught in this bucket. Based on our research question of interest, we'll tow this plankton net very slowly for a certain amount of time. As you can imagine, as we pull this slowly through the water column, the water, as we head into the current, is passively filtered through this 100-micron net. The reason why we go slowly is, as we learned in class, a number of zooplankton are motile, meaning that they can move in the water column. So we don't want them to anticipate this giant net coming at them and move out of the way. So if we go at the right pace, we can capture a good representation of the zooplankton within the water column. Based on that time and the diameter of this ring, we can estimate the amount of volume of water that we've just sampled in this plankton tow. Later on today, I'll bring this sample back to Gold Simpson and we'll look at it together under the microscope to see what the zooplankton counts, so the density of zooplankton, as well as the diversity, so the number of species of zooplankton within the water column here at the Biosphere 2. And when we combine that with the information about the volume of water, we can divide our counts, our densities, by the volume of water and estimate the amount of biodiversity of different species within that particular water sample. So we can get quantitative estimates of the density of zooplankton within the water column. Okay, we're going to deploy it. Okay, now we're going to paddle into the current and tow very carefully. This is generally not how you would do it. You would do it on a boat with an engine. Nevertheless, so we'll take a look at these samples under the microscope and identify what's in the biosphere ocean right now. We've made it back to main campus and we're going to look at today's sample under the microscope. So here I have our zooplankton sample, or 100-micron mesh sample to see what zooplankton we have here at the Biosphere 2. So I'll take a look here under the dissecting scope. And we have a foram. So let's take a look here at the computer and take some pictures. So this is a species of foraminifera, a planktonic species that has a sort of body form that's a little bit of an evolutionary mix of a planktonic and benthic foram. So it's really exciting to see one of those here at the Biosphere 2. The other thing we found in our sample, of course, is a lot of hermit crab larvae. So this tells us that our hermit crabs have been reproducing recently in the Biosphere 2, which is really exciting. I hope you enjoyed the virtual field trip at the Biosphere 2 ocean as much as I did. Of course, we had a few technical difficulties of trying to row and take a plankton sample at the same time. But nevertheless, I think you guys got the sense for what we would have learned on the oceanographic vessel in Southern California. You saw us demonstrate plankton tow of zooplankton, so a 100-micron net, a Secchi disc for turbidity and water clarity, a Van Dorn water sampler, and finally a YSI, which is very similar to the CTD that gives us the conductivity, temperature, pH, ORP, and dissolved oxygen profiles with depth in the water column. That concludes our virtual field trip with the Biosphere 2 ocean, the largest enclosed mesocosm focused on coral reef research.